The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, folks, lots to do. Exams on 24th. Today is the first. 23 days to go. Lots to cover. I actually think that this is a sort of exam where if you really understand the fundamentals, everything follows. It's not, there's no memory, right? Yeah, you need some memory, but it's not a test of your memory as much as a test of your logic. So we need to keep plowing ahead with the logic and get to a place where we can rework everything. All right, last class. Let me turn more of the lights on here. Last class we did, what did we do in the last class? I've forgotten. Seems ages ago. Anyone remember what we did? Inelastic collisions, yep. So actually elastic collisions first. So we started with momentum. And I told you that bizarre pimento joke. It's true. I didn't make it up. I make up some stuff, but that's true. And I forgot to get the I'll find you the PDF file. So that's momentum. Then Newton's laws. In particular, we talked about the strong form of Newton's law, the third law. And we did the work energy principle. I have a comment about that. Some of you have some questions. Then we did collisions. And did we do elastic collisions or inelastic collisions? Both. And the difference is in the coefficient of restitution. If it is 1, energy is conserved. If it is 0, energy isn't conserved. Is momentum always conserved? Yes. Okay, so that's what we did in the last class. Today what we're going to do is I'm going to just spend a few minutes tying up some loose ends from the last class. So I'm going to start with a problem. So first, loose ends. I wonder whether, why is there a role in football called a tight end? Anyone? Any football players out there? You can tell me later. Then we're going to do a problem, an example problem. And then I'm going to introduce you to equations of motion formally. I've hinted at them through emails, etc. I'm going to really nail it today. You kind of know what it is, but I want to do it formally once. Then we'll do another problem. And then we'll do angular momentum. This is a very cool concept. All right. 2 loose ends I want to tie up. I'll just do it here. The first loose end I want to tie up is something you know, but I just want to tell you what it is again. It's the concept of impulse. I'm assuming you all know what impulse is, but let's do it carefully anyway. It's very simple. First of all, what are the units of impulse? Anybody? Say it again. Newton seconds. Is there another way to view impulse? That's correct, by the way. Anything else? Any other way to view impulse? Newton seconds is correct. Yeah, kilograms meters per second squared. It's the same thing. But the reason it's useful to say it both ways is impulse is the product of force and time. It is also a change of momentum. Done. Right? It's the same thing. And the way to think about it is when you think of two particles, let's think of point masses heading towards each other, and then they collide, and if it's inelastic, there might be some deformation involved, and then they bounce off each other if it's inelastic with smaller velocities. Then you can plot, let's call this A and this guy B. You can plot the force from B onto A. That is, the force felt by A. And it's going to be equal and opposite to the force from A onto B, right? You can plot that force as a function of time. How will it look? Assume it's inelastic. How will it look? So initially, when they're not in contact, the force is 0. And then they kind of touch, and then the force goes up. And then both of them deform, the force goes up. And then they start bouncing away, then the force goes down. Eventually, they separate. That's force versus time. Right? Nothing very profound. Impulse is equal to the integral of f dt for the period of the collision, which in this case we can just go minus infinity to plus infinity, right? But you need to be careful because there's some other collision. You need to be very careful about what you mean by the impulse. It's for that event. And effectively, it is this area. And all that impulse says is that force is changing momentum. It's changing the momentum of A. So that's the change in momentum of A, right, over that period of time. So the area under that curve is the change in momentum of A. So it is also change in momentum. Write it here. Okay, if you can't see that, that's change in momentum. And it's simply f dt. And the units are f Newton second or kilograms meters per second. Same thing. Yes? Nothing profound? Now, if the collision is instantaneous, if the two spheres are infinitely rigid, what's going to happen to this guy, to this shape? Yeah. The width will go down, but because the total impulse needs to remain the same, the height stays the same. The height has to go up. Right? So it goes to infinity. And that is our idealized view of an impulse. So you can think of these elastic collisions as bam, right? The two particles rush up to each other, they instantly shake hands, they exchange momenta, then they head their own ways, right? The net amount of momentum exchanged is transmitted as one infinite spike of force for 0 for a very short period of time. And that's kind of the extreme version of looking at impulse. Okay? Impulse is a shorthand. It's a laziness that we indulge in to say, yeah, they collided, something happened, they exchanged momenta, here's a momentum change. And since momentum change is a long word and it sounds kludgy, we make up a word, we call it impulse. That's it. All right? So you've seen that before, and that's what impulse is. So let's say there's a basketball, or actually that hurts, a soccer ball heading towards me. Have you ever tried kicking a basketball, by the way? It really hurts. Don't do it. But anyway, a soccer ball heading towards you, right? And let's say there's no drag, nothing, no losses. And unfortunately, it's an infinitely rigid soccer ball, so that might be painful too. But anyway, it's heading towards me, 1 meter per second towards me, right? And I kick it. I rock back because my momentum is conserved as well. But let's ignore me for the moment. And that ball heads back at 1 meter a second. What is the total impulse? And it's 1 kilogram. Say it again? That's right. It's 1 meter kilogram, 1 kilogram meters per second, heading this way, initial. Afterwards, it's minus 1 kilograms meter per second because it's heading the other way. 1 minus 1 these days is 2. So the impulse I imparted was 2 kilograms meters per second. That's the impulse done. All right? Very simple concept. No, nothing very profound about it. I just wanted to put that to rest. The second thing I wanted to say, I'm going to say it now, and then I'll say it again later on more formally, is, let me ask you a question. Does energy conservation give you a different equation than F is equal to ma? Think of a 1 degree of freedom system, right? A particle on a line, on a straight line. I apply force on it. It's going to accelerate. F is equal to ma. Right? Let's say that the particle it's only going to move on a straight line, like a train on a track. It has 0 velocity. I apply a certain force. For example, I turn on a rocket, which applies a constant force for a second. Right? I look at the final velocity, and let's say it's going uphill a little bit. I can formulate one equation which equates kinetic energy to increase in potential energy and the work done by the force. Or I can just take the force and write F is equal to ma and figure out what the final velocity is. Will I get the same equation or not? What do you think? Yes, absolutely, fundamentally, unavoidably, yes. It is the same thing. It's the same thing, absolutely. All right? Energy conservation is just an easy way to do force balance. When it's easier to do energy, if you want to get one equation out of it, and it's 1 degree of freedom, that's it, you're done. Look, what I derived for you in class last week, and sometimes there's a dude outside kicking a tree. Seriously, I'm not joking. Whatever. Anyway. Right? I didn't make it up. He's kicking a tree. Look, here's what I said to you. Very simple, guys. F is equal to ma. That's an equation of motion. Don't worry, we'll do this more formally now in a minute. Right? You know that. That's Newton's equation of motion. That's the only equation that exists. Everything else follows from this. Energy is simply doing this. Integrating this and integrating this. So the equation doesn't change. Get it? It's the same thing. And that's what I did for you in class. The way I did it was I said F integrated over dr, right? And I wrote m, this thing, as v dot. And I said dot v dr, sorry, dt. Because dr is the same as v dt. Remember that? Okay, and I'm just going to do it very informally. This, right, is m v dot squared over 2, kinetic energy. You understand? And this, F, if there's no external force except a potential energy kind of term, this becomes del of potential, dr. That's just going to be potential energy difference, delta potential energy, right? It's the same thing. So Newton's law integrated gives you energy. That's it. It's the same equation. If you get new information, you're in trouble because particles can't be in two places at the same time, at least in Newtonian physics, right? So it's very fundamental that I want to make sure that you're all, with me on this, that you understand what I'm saying, that energy is fundamentally the same as Newton's law. It's just a different form of the same equation. Now, the problem is, when you have 1 degree of freedom, you just need one equation, everything is hunky-dory. But if you have 2 degrees of freedom, you need 2 equations, energy only gives you 1. If you have 5 degrees of freedom, energy still gives you only 1, because total energy is conserved. Right? You still need 4 more equations. So that's why you have to go down the Newtonian path of writing F is equal to ma 5 times, right? Yeah, one of them you can get energy, but the other 4 you have to get by writing F is equal to ma. Get it? You understand? Yep, Levi.
So when you're doing the F is ma, the two equations of motion you get are in your two directions you're asking for. Right?
That's right.
But when you're doing energy, which one do you get?
You get total.
You get total, right? So
Right. Yeah, that's good, right? So think about it. F is equal to ma. We'll do a problem now. Okay, don't worry. We'll nail this, right? F is equal to ma. F in the x direction is equal to a mass times acceleration in the x direction. F in the y direction is equal to mass times acceleration in the y direction, right? When you do energy, you're looking at the magnitude of the velocity, right? It's v dot v. So they all kind of get bung into one. They all get combined. So you just get one kind of overall equation. Get it? All right. So let's solve a problem. So that's so those are the loose ends. Okay. So I've told you about impulse. I've kind of started talking about energy, but now let's get into energy. Well, let's solve a problem, and I'll give you the equations of motions more formally now. Yep. I beg your pardon. So v squared. Right. It's v dot. Yeah, it's v squared. Actually, the way I would have written that, just to write it correctly, is look at your derivation, but this is how I would have written it. Okay? I think. Yeah, whatever. You get the idea. Okay. So yeah, please look at my derivation. I just scratched something out here just to give you a sense it's integral. Look at the derivation. So here's the problem we're going to solve, folks. First problem using where we're going to actually solve, not just find the acceleration, but we're going to find a dynamical equation. It's okay to say dynamic equation or dynamical. They're both adjectives, by the way. All right? Okay. So the problem is this. You have a quadrant of a circle. Think of a ski ramp, except it's circular. But here it's completely vertical, right? Now, you have someone, let's call it, we'll treat that thing as a point mass. When I say point, I'm referring to a point mass here. But it could be a skier. In other words, we're ignoring the fact that this person is actually a three-dimensional entity, and treat this person as a point. And it's stationary. Actually, doesn't matter. Let's assume it's stationary for the time being. Doesn't matter, right? And the question we ask is, we're going to just push him a little bit. And we want to know where, if at all, this person will depart from this ski ramp. In other words, separate. Right? And for sure, they're going to depart here. Right? If the circle continues, they're going to fall off. But will they depart earlier? And that is the first problem that we're going to solve in dynamics. So I want you to think about it for just a second, then I'm going to ask you a question. So first of all, the question I'm going to ask you, but think about it for a second, is will they separate or not? Anybody? Will they separate?
Yes.
Why? Why? Just think about it in English. Why would they separate? Just in English. Forget, you don't have to use equations. Say it again? That's good. And so what will happen when they separate? You're right. I'm asking a deeper question now, next level question, which is, yep, Claudio.
The force between the two objects, normal force, will become zero.
That's right. That's right. Okay? So the force between the two objects, which is the normal force, will go to zero. In other words, the skier's knees will stop flexing, and in fact, the skier will find that he or she would need some sort of attachment to the snow to stay on it. Right? It's like driving over a curve in the road, right? A vertical curve, a hump in the road. All right. So how would we go about solving this? Okay. Find the velocity as a function of angle. Then English. That's good. You're exactly right. And then what would we do? Yeah. Well, Claudio, you've spoken. You've both spoken. Someone else. Someone in that quadrant. Yes.
Find the theta where the normal force or the force of gravity is exceeded by the centrifugal force.
Yeah, kinda, right? That's right. That's right. Okay, that's correct. So find the angle at which the centripetal acceleration is not sustained by gravity, kinda, right? Centripetal acceleration is the very minimum acceleration that the component of gravity in that direction, not really gravity, but the component of gravity must provide to keep them attached, right? And if gravity doesn't provide that, then at some point they're going to fly off, right? Okay, so how do we start? How do we start this? Let me check. I have it in my notes. Yes, I know how to start it. How do you start it? It starts with an F. It's a word that starts with an F. Yeah.
Design a frame, fixed frame, and moving frame relative to the particle movement.
Yeah, we'll have to do that, in fact. But actually, it's a 3-letter acronym that starts with an F. Yeah. So, from here on, we enter the land of 3-body diagrams, all right? And from here on, pretty much everything you do, when in doubt, draw a 3-body diagram. In fact, in life, right? For example, if a cop pulls you over, as it happened to me yesterday, and you don't know what to say, just draw a 3-body diagram, you know? And then try and argue your way out of the ticket. Okay. I did it. Didn't work. He let me go anyway. But anyway. So, a 3-body diagram. So what's a 3-body diagram? It's very simple. We're going to identify all the forces on this thing. Why is it called a 3-body diagram? Anybody remember? Huh? That's right. What you do is you remove all the supports and you draw this thing as if it was suspended by strings. And you figure out what the forces in the strings need to be to keep it suspended there. That's exactly what this is. In fact, that's the cleanest way to think of a 3-body diagram. Remove all supports and replace it by strings and figure out what the forces in the strings should be. So let's do that. So let's draw it for some position here. And let's call this, and Andrew, I'll come back to what you said. So what you said was correct, right? But that's the next step, and I just want to break it down a little bit. Let's call this theta. By the way, let's call the radius of this rho. And let's draw the free body diagram. So the free body diagram for this. What forces does this guy feel? By the way, let's label them. This is O. I'm going to call this point Q. Okay. What are the free body, what are the forces on this particle as if it was, what forces would you make up? You know them, come on, say it.
Gravity.
Gravity, yep. So let's assume, look. This has to be the worst design room on the planet. Well, no, there are others, but it's pretty bad. All right, so gravity. Right? By the way, I can now, let's introduce our first frame. I'm going to call this guy A because I need some directions. Right? So I have an A1 and an A2. Right? So gravity is minus mg A2. Right? It's okay. We'll come back to that. What are the other forces on this? Normal force. Right? And the normal force will point which way? That way? Okay. So a normal force N. Okay. So, total force is equal to what? Let's just use vector notation for the time being. Yeah, I'll write it for you. And when I write it, you'll say, I think you'll agree. Total force on particle P. I'm going to use it in full notation. I'm going to use little f for force. Little f because it's a particle. Later on, when I do bunches of particles with rigid bodies, I'll use capital F. P because that's the name of the particle. Oh, is it Q? Oh, okay. You know what I mean. Okay. all right, just checking, just testing, okay, is equal to minus mg a2 plus, and now, Andrew, I'm going to define a second frame, because it will also come in handy for another reason. I'm going to define this frame, which, all right, but the way I'm going to define it is, I'm going to pivot it right here, all right? So it's actually pivoted. It's not moving with the particle, it's just pointing towards the particle. You understand? Very important. That frame is actually, I just don't have space to draw it here. It's pivoted right here. So this is point Q. So this frame is here. Now frames can move, but the point is it's not kind of accelerating, it's just rotating to follow the particle. It's like a gun pointing at the particle, but right from point O. You understand? Right? So in fact, what I could say is that there is this frame which is a transparency B, this frame which is transparency A. B rotates in A, and the point of B that stays, that does not translate with respect to point A, is point Q, and they coincide right here. So please be very clear, all right? Do you want me to redraw it with B right there? Will you remember this? Because if B is moving, then the accelerations, I'll have to do it differently. So I'm drawing it that way, but be careful. You understand? Please, okay? All right. So the net force is, correct? Okay, F. What do I do now? Levi.
You can put your all the way forces, or at least basically you care about the forces in the beam. So you can break up your mg force and find out what the beam component is.
Okay. Okay. So at this point, what I'm going to do is I'm going to be more general. So because what you're doing is you're using, I told you about the problem, so you're kind of looking ahead, which is good, which is the skill you'll start leveraging, especially in exams, to minimize your work, which is great, right? But what I'm going to do is I'm going to figure out the equation of motion of this particle in its true and most general sense. You understand? So I won't break it out and all that. I'll write it in its full and most general sense. So what do I do now? What's the equation? What is Newton's law? F is equal to ma, right? So I just figured out the F. What do I need to figure out next? A. So let's try and figure out now. So we want right? This is what we want to do. Actually, it's a little f. Sorry, q, right? This is what we're trying to figure out. We figured this guy out. M is a scalar. We know what it is. So now we're going to try and figure out AQ, and that's a fundamental Newtonian method. Okay? Figure out all the accelerations, figure out all the forces, equate F is equal to ma. So now I want you to tell me what AQ is. Anybody? How do we do that? What? Sorry, I can't hear you. Yeah, super ultra cool magic formula, that's right. Why? Okay. So how do we use it? Let's write it out. Shall we? Okay. So the way to think about it is, remember this B, right? It's kind of here and just rotating. B is not translating with respect to A, it's just rotating there. So think of A as the Earth. The space shuttle, or the Frisbee or whatever, is stationary in the sense that it's right there. It's not actually moving, it's just rotating, right? And there's a particle like its nose that we want to figure out the acceleration for. So what is the super ultra cool magic formula? It is, and I'm going to run out of room and I'll finish it up there, is A AQ. Can you please read it out to me because I'm very forgetful? I need you to go back and look at your notes and tell me because this is part of the exercise. We're going to use all that stuff, right? First of all, how many terms are there in the ultra? 5. Right. First term, let's reconstruct it or look at your notes. First term is can you imagine no one's named this formula? It's amazing. You know, I mean, I had to make that up. I think it's a cool name. But, you know, you'd have thought that, you know, someone would have given that name to some buddy of theirs, right? Plus what? I'm just writing it out. Yep.
Why is point O also labeled as Q?
Because, very good point. Because I was thinking ahead when I wrote this problem. Remember in the, let's examine this a little bit, right? So we're trying to apply the Frisbee problem here. In the Frisbee problem, you have, you know, Sanjay's garden. You have the Frisbee. It's hurtling through space. We call that B. Oh, did I label that Q? Oh, so I'm sorry, I screwed that up. That should be P in the formula. Sorry. But let me finish what I was saying. I think that's what you were asking, but it's a long answer, but I'll give it to you anyway. We call this P, we call this Q, right? And that's what the super ultra cool formula was for, right? But what I'm going to do is say the Frisbee actually stays pinned right here. So it's just spinning. And then I'm going to use the formula. That's what I was trying to do. But I'm sorry, I miswrote that. That should have been P. This should have been P. I apologize. Okay, in my notes I had Q and I changed them around. I apologize. Okay, what else? Anyone? Say it again? Oh. Plus? So this is the Coriolis effect. What else? This is the Euler form, Euler term plus all right. Now I'm doing in a painstaking way something that you guys intuited right in the beginning, which is there's got to be a centripetal term, right? But the reason I'm doing it in a painstaking way is I think all of you actually also forgot this term. All right? In the general sense of the problem. Now, it won't show up in solving this problem, but there is this term. But it's okay. Let's just do it painstakingly. Okay, what is A acceleration P in our case? What is B acceleration Q in our case? What is this guy? The Coriolis term? Get it? Yes, B is rotating with respect to A, but Q is not moving with respect to P in frame B. Should that be a what? Oh yeah, it should be. Oh, you guys are good. Okay, but Q, I mean Q is not moving with respect to B. Yes? There's no Coriolis term. So that only leaves these two terms. So let's compute them. So let's compute them. So what is A acceleration P now? Sorry, Q now? So here's what I'm going to do. This is going to be your snap quiz. It's a very simple snap quiz. Take out a sheet of paper, write it out for me. This is only like 2 or 3 minutes. Yep. Hold that thought. Okay, so guys, excellent question. Right now we're simply analyzing and trying to come up with an equation of motion in the most general sense of the ball as it goes down the ramp before it leaves the ramp. We're just trying to write the equation of motion. All right? And then we'll do the smart thing, which is figure out when it leaves the ramp. But right now we're writing the equation of motion. Good? Okay. The snap quiz comes in 2 halves. So use a big sheet of paper use a large sheet of paper if you can, because I'm going to ask you to do something on the back side. How are you doing? Is it easy? Let me give you hint number 1. I know the particle is falling, right? I know it's going to slide down. But since I label theta as going up, right, increasing as it goes up, formulate the equation of motion as if it's going up. Don't get confused by that. The negatives will take care of themselves. Get it? Just a hint. Right? When theta increases, the particle is going up. I know it sounds counterintuitive because the particle is really going to come down. But don't worry about it. Write it that way and it will come out negative. Okay? In general, any non-standard coordinate or parameter, assume it's going to increase. And if it's supposed to go the other way, Newton's laws will drive it to a negative. Okay? Just don't worry about signs that much. Don't double think. Done? Yes? Okay. So let's write it out. Let's solve it anyway. What is A alpha B? Quick. Okay. Cross RPQ. And what is A omega B? And what does it come out to be? Yeah. Is this correct? Yeah? The correct? Oh, that's B1, yeah. This one? Oh, that's right. It's coming inwards. Yep. Okay. Now, in English, what is this term? And what is this term? Okay. So now we have both F and AQ. So what is the equation of motion? It is, get this, it is simply forgot one term, which is the M. Make sense? That, folks, is equation of motion. There's no magic here. I just did F from free body diagram. I did A from all the stuff you've learned. And I wrote F is equal to MA in vector form. Done. That's it. Right? So let's do some, let's ponder this a little bit. Yep. hint in the following sense. We just assumed a certain direction of theta. This is a differential equation. Okay, so this is actually where I wanted to go with what I was going to say anyway. This is a differential equation. When you solve this differential equation, you'll get some function, right? For example, if you solve mx double dot is equal to constant, x double dot is equal to constant over m, x dot is equal to, integrated once, x, you solve the differential equation, you'll get, in this case, theta is a function of time. And by the way, it'll go the other way. Theta will become more and more negative over time, so it's falling. So trust and have faith that that's how things will work out. You understand? So it's very simple. There's a differential equation. Differential equations have the same principles. Unknowns must equal number of equations, right? Solve the differential equation, which we won't do yet. Well, we'll solve it for this one because it's easy, right? But once you solve the differential equation, you'll get theta as a function of time. You understand? And that will just happen to have a trajectory, theta as a function of time, that's negative. So if you solve this differential equation, you'll end up with something that looks like this. Theta as a function of time with time, right? And you'll find that theta is, the initial condition will say theta was at pi over 2, which was, it was at the top of the ramp. And what's going to happen to it? It'll decrease, right? And at some point it separates. And that's, once it separates, our equations of motion, the way we wrote them, are no longer valid. Because we assume that the particle was in constant contact, right? But this is what you're going to solve for. Now, right now, in this first piece of the course, we concentrate entirely on writing as many equations of motion as there are unknowns. That's the entire focus before the first midterm. We don't solve them. Yeah, we'll solve them once in a while just to give you a taste. In fact, I might solve them here, right? But the objective is simply to write the equations of motion. That I want you to understand. The second third of the course is Lagrange. It's just an easier way to write the differential equations. But we won't solve them either. It is in the last piece that we actually solve the differential equations. Formally. Informally, we'll try and solve it here as well. Okay? Now, how many equations are there embedded in this? 2, because this is a vector equation. There are 2. How many unknowns are there? Which are the unknowns? Excellent. There are 2 unknowns. One is this, and the other is this. Okay? So this is very interesting. In 2-dimensional space, how many degrees of freedom does a particle have? 2. But usually, they're both kind of dimensional degrees of freedom, right? So the unknowns should be like an x and a y, right? Here's what happens. If you constrain something, all that happens is one of the dimensional degrees of freedom goes away, but an unknown force makes an appearance. You get it? You understand? So every time you constrain something, yeah, you'll take out a degree of freedom, but an unknown force is going to crop up, right? And I'm going to write out now for you something that's fairly profound. I want you to think about it, because there are many ways to kind of go about it, and you'll say, does the math work out? In the end, you need as many degrees of freedom, as many unknowns as there are equations. And we ended up there, right? But now let me tell you how we ended up there. If you have a system with m points and n rigid bodies in 2D space, right? In general, how many degrees of freedom does it have? M points and n rigid bodies. Come on, you know it. M points, n rigid bodies. So, in general, if you have m points in 2-dimensional space, how many degrees of freedom? If you have n rigid bodies? Okay. That's the total number of degrees of freedom of, yep. Say it again, sorry. Sam? Okay, all right. So in general, you're going to have m points, n rigid body. You'll have 2m plus 3n unknowns, right? Degrees of freedom. In general, right, you will get, now, a point, when you write the free body, do the free body diagram and write equations, you'll get 2 equations, right? So the number of equations is going to be 2m plus 3n. Because for every point you'll get 2 equations, and you'll see later for every rigid body you'll get 2 equations plus the torque equation, that's 3. So things balance out. You understand? So in the end, when you've studied rigid bodies which have points and rigid bodies, you will always end up with as many equations as you have unknowns. You understand? But now I want you to pay attention, really grit your teeth. It depends also on whether you want to call out the kinematic constraints implicitly or explicitly. All right? Let me explain that. It's profound. If you don't get it, as you do the problems, you'll understand this anyway. You'll understand it at some gut level. I'm trying to articulate it for you. Look at this guy. Really, that point has 2 degrees of freedom. It can move left or right, can move up or down, right? But by constraining it to be on a slide, we're saying the distance from the center, as long as it's on the slide, must be rho, right? Now, naturally, we could have said, hey, write an equation of motion with x and y as the degrees of freedom, and we'll impose the rho constraint later. Or we could have picked a natural non-standard coordinate, which is what we did. We just picked theta to enforce it kind of implicitly, right? So if you pick coordinates that are natural and you enforce the kinematic constraint implicitly, this is what will happen. If, however, you pick the coordinates not, awkward coordinates, you will get k extra unknowns in terms of the unknown forces, but you'll get k extra constraint equations. You understand? But again, number of unknowns is equal to number of equations. Get it? If you don't get it, I'll say it all over again. Do you want me to say it all over again? Because I'm very happy to do that. Do you want me to say it again? Okay. Forget that. Just look at me, right? How many degrees of freedom do I have in space? Assume I'm a rigid, I'm a point. 3 in space, right? Now, as I stand here, can I move up and down? I mean, let's say I can't jump, right? So how many degrees of freedom do I have? 2, right? Now, I can ignore that up-down degree of freedom and just say my z height is equal to 0. And I write 2 equations of motion. I have 2 unknowns. I'm done, right? Or I could say, no, Sanjay has 3 degrees of freedom, x, y, and z. Oh, by the way, z is equal to 0, right? I called out that z, made it an unknown, and then I said it equal to 0. That's 3 unknowns and 3 equations, right? That's a very kind of a silly example, but in fact, that's an example of how, by explicitly calling out a variable and setting it to 0, I bumped up the number of degrees of freedom by 1, right? And then introduced one more constraint. Or the natural thing is to say, forget z, he isn't going to move up and down because he's on the floor, right? It's 2 unknowns, 2 equations. Get it? So in this case, it's a little more complicated. Really, the point, if it could travel up and down, has 2 degrees of freedom, right? So really, I need 2 unknowns, and there's an unknown force, so there'll be 3 unknowns, right? And I can write 3 equations. 2 from f is equal to ma, and 1 is that the constraint that the distance from the center must be rho. Or I could just naturally say forget that and collapse it and just go for the minimum number of degrees of freedom, right? So essentially what I'm saying is, look, if you don't get this, it's okay. It'll become clearer and clearer over time. The point I'm trying to make is that depending on how you parameterize the configuration of something, whether you pick minimum parameters or you say, forget it, I'll go with some other parameters, some of the non-standard coordinates, and I'll put constraints, You might end up with different numbers of equations, but you will always end up with as many equations as there are unknowns. Got it? Okay? You're going to have to ponder this and think about it. But in the end, the objective of this course is to write equations of motion. Count the number of unknowns. You better have that many equations. In the first, third, and then the second third of the class, we just want to make sure the balance is met. Then we'll figure out how to solve the simultaneous differential equations, right? And that's the end of 2003. That's the third piece of this course, and all of 2004. You understand? Okay? So I will never say, hey, in the first, at least the first third, I'll say, just make sure they're equal. You have, and you can, you'll scratch around it. Initially, you'll be like, was it implicit? Don't worry about it. Just do it. And, you'll say, if you see that the number of unknowns exceeds the number of equations, there's probably some kinematic constraint or something you forgot. And you'll find it and you'll write it down. Okay? How are you guys holding up? Okay? This takes some pondering. You will ponder it, you will get it. I'm confident. But sometimes it takes a little longer to get it. Okay, now I want you to do the second piece of the snap quiz. I want you to solve this problem, the same problem, using energy. Oh, by the way, we didn't solve the problem. We didn't solve it. I beg your pardon. Let's solve it. So what we're going to do now is we wrote it in vector form. Now let's write this equation in motion in scalar form. In order to do that, we can rewrite A2 if we want in terms of B1 and B2, right? And then everything becomes B1 and B2. We can split it up into two scalar equations. So look at your notes and tell me, what is A2 in terms of B1 and B2?
B1 sine theta plus B2 cosine theta.
Can everyone verify and make sure you agree with this? Seems correct? Okay. All right. So let's rewrite this. So it's, I'm going to try and do it really quickly. This becomes, so there'll be a B1 term, so minus mg sine theta plus n. I'm trying to do all the B1 terms together. And then all the B2 terms together. Tell me if I'm doing this right. Okay, I'm doing it on the fly with you guys. This will become Is this correct? Anyone disagree with me on this? Okay, yep.
You want to simplify it as possible, or just simplify it?
Okay, when you write the answer, right, if you have, even if you write it in vector form, Ajay, let's reach a consensus here. If from a grading point of view, if you write the equation of motion in vector form, that's good enough. If you say find the equation of motion, if you write it in vector form, that's good enough. All right? Now, we don't even have to pull them apart if you don't want. But if we ask an end goal, which is a step further, for example, figure out when the thing's going to separate, then you've got to go all the way. You understand? So, but the end goal here was to figure out when they separate. Okay? Yes? That's right. So now let's examine these two guys. What is this saying? This is saying that the component of the force this way, right, tangential, is going to be the Euler acceleration term, basically. Right? Makes sense? And this is saying that gravity plus normal force is equal to the centripetal acceleration. So gravity plus the kind of the component of the normal force is centripetal acceleration. Beautiful, right? It's exactly what we expected. So it's exactly what someone was saying earlier, right? You were saying that earlier, right? Which is this is exactly what we expected. We just did it right, brute force, correctly, and it all worked out. Okay. Now let's solve them. I know that solving isn't really a part of this first third, but we asked you to solve it in this particular case because it's a simple one. So let's solve it. So what do I do next? I'm trying to figure out when the skier takes off. What do I do next? That's right. Set this equal to 0. Okay. Okay. And we get right? And for this, we can go okay. Is there any way to simplify this? What? How would you simplify this? Yeah, you would have to integrate it, right? And the way you would have to do it is this is a differential equation. Okay? It's a differential equation. And by the way, this is separation. So the question I'm not going to do it now because now I'm going to show you the energy method. I'm actually going to ask you to do it in a snap quiz, right? And I won't do this right now. I'll solve it and give it to you as a handout because it's a pain in the neck. But I want to show you that this is how the differential equations would go. And let's kind of set it up. So this is the theta of separation. This is what we're trying to get at, right? So what we're going to do is first solve this. You understand? Get theta as a function of time. And then solve this and figure out theta separation. Got it? So how do we solve this? This is actually a differential equation. d2 theta upon dt squared is equal to, m's will cancel here, minus cosine theta upon rho divided by rho. It's a differential equation, folks. Times g, where's the g? Here. Right? And do you know how to solve this? Huh? Go ahead. Yeah, basically what you're going to do is, the long and short of it is you'll propose some solution. For example, you'll say, assume theta is, some function, and you're going to propose it, solve it twice. And you'll basically integrate, right? So I'm not going to do it right now. You would solve it and then get separation. But this is how you write the differential equation. You can see that writing out all the differential equations and solving them can be somewhat painful, right? So what is a nice way to solve it? I'll solve it for you and give it as a handout. I want to get to the last part in this class. You can solve this. You'll get a handout on this. But now the question is, it's a pain, right? You gotta solve this differential equation. I want to get the separation angle. Is there another way to do this? I'm sorry? Yeah, that's exactly what you would do. That's what solving it is, right? You would guess theta as some function, solve for it, right? And then from that get the separation angle. But is there an easier way to, and by the way, solving differential equations is often also called integrating a differential equation, right? To make it more algebraic, right? But this is very painful, and it's just kind of a lot of differential equations. And yeah, you can do it. In this case, actually, you can do it in closed form. I'm not going to do it right now. I'll give it to you as a handout, right? Because the point of this is not to show you how to solve differential equations right now. The point of it was to get to that separation angle. Is there another way to do it? Which will give me the same answer, energy, right? Because energy, the whole point was, we kind of integrated this in advance, right? You'll only get one equation from energy, but it's for free almost. So let's do that. And let's try and figure out now from energy, and that's your other snap quiz, right? Remember I said I'll ask you again? I want you to figure out an energy formulation for solving this problem. Go. And I want you to struggle a little bit, right? For example, potential energy. It's actually a potential energy change. What is the potential energy at the top? Yeah, but why not just assume it to be 0? Just assume that to 0. Just make your math a little easier. You understand? Or it doesn't matter. Take bottom. Actually, yeah, it doesn't matter. You can do it in a number of ways, but try and solve it. I want you to struggle through it, and we'll solve it right now. Will energy give a different answer than if I just integrate the heck out of this? Or is the energy equation just a restatement of this equation? Anybody? Is there any new information in the energy equation compared to this? There is not. It cannot give a different answer. It's the same equation written another way. It's some higher, it's just these things kind of manipulate it to look different. That's it. There's no new information. Yeah? Very simple, right? And Ted, I saw his notation he had in his head, and he just wrote it down. Just come on up, Ted, right? So what he did was, what we're going to do is, we're going to find the potential energy at the top, which is, we can set it to 0, 100, 2, 16.5, whatever we want. It's just a number, right? And the kinetic energy at the top. What's the kinetic energy at the top? Assuming it starts from rest. Then, as a function of theta, we're going to find the potential energy. And we're going to find the kinetic energy, right? We're going to equate them. We'll solve for the velocity, and we'll see if where the reaction vanishes. And that should give us the answer. Okay? So Ted's going to follow one path of solving this problem. No, but how do you separate variables? You integrated what with respect to time?
Yeah.
How can you integrate that with respect to time?
That's true.
So let's figure it out and write a little handout. So, Ted, you're going to have to state what you're doing. Yeah, take with the lecture, man. You need to be a little weird because I'm weird too. So.
You equate the change in potential energy to the change in kinetic energy.
Okay. So what's the potential energy at the top is 0.
Well,
did you write it as 0? How did you write it?
MGH.
Okay, you took height. Okay, and height was the same as rho, right?
And then, as then we defined y from from the ground to the top. So then the change in height going downwards is h minus y. I guess that's going upwards. So this is the change in potential energy.
Okay.
So this is the change.
So has the potential energy gone up or gone down?
What?
Has the potential energy gone up or down?
The potential energy is decreasing.
Decreasing, okay. So the decrease in potential energy must be equal to the increase in kinetic energy, right? So what is the kinetic energy? Half mv squared. Okay, okay. So let's rewrite that just in terms of, just stay there. I'm going to use this space here and just kind of comment on what Ted did there. So basically what it did was half m a vp squared. Remember, squared is the same thing dot producted by itself, right? Is equal to change in potential energy, which is m g, and in our notation, in this notation, that is this height, right, this gap, and that is rho times 1 minus sine theta. Okay, keep going. And then you just solve for AVP, the magnitude of AVP, which is velocity, right? I'm just going to write that as velocity, is equal to root of m's cancel.
You don't need to take the root.
You don't need to, but I'm just solving it for what it's worth. Right, we don't need it because we'll use it in its full form. 2gh, 1 minus sine theta. All right, then what do you do?
Okay, so then at the point where at least there's no normal force, which means that the sort of radial component of the force due to gravity is equal to the centripetal force needed to keep it going in a circle.
Okay, so hold on, let me just comment on that. That is this guy, right? He's just taking components along the B1 direction. You understand? So he's saying N1 minus mg, you know, and it'll be like a sine theta, right? Will be sine theta? Yeah, go ahead, keep going, yeah. No, just write it down. Right.
Okay, so you have the centripetal force is m v squared over h.
Mm-hmm.
And so that has to be equal to the radial component of gravity. So you have, I think this one. So I think this is energy cos theta. And this is energy sine theta. Right? Yeah, I think so. So this becomes equal to mg sine theta.
That's correct, by the way, yeah. Mm-hmm.
So now you have two, you want to solve for the theta, where this is true. This is only true if there's one point where it's about to leave. We know the m's go away, and in terms of everything else goes away. So you can just solve it.
I'll write the final answer.
So theta is equal to the arc sine of 2 theta.
Good. Excellent. Thank you. So we'll go to lunch. You're free today? I'll take you out for lunch today. Okay, done. Okay. It's amazing what people do for a free lunch. Include stand on a stage. Great job. Thanks, Ted. That's exactly right. So let me kind of just reinterpret that, right? So essentially what he did was, he used, are you clear up to here? Up to here? That's what I just wrote, right? So essentially what he then did was, he said that, look, in this term, we calculated the force, net force, right? And if you just do a force balance along the B1 direction, right? Essentially what it'll come down to is that the net force along the B1 direction is mg sine theta minus n is equal to, sorry, mg sine theta minus m, how do I say that? Let me do it right here. So it's accelerating downwards. So mg, so the force on it is mg sine theta. That force is N. So the force balance is, help me out here, Ted. How did I do this? I'm trying to interpret in your words here. mg sine theta, right, is equal to, in your words, excuse me, let me just reinterpret it here. No, I'm just trying to rewrite it in your words. Say it again?
Oh.
Yeah, is equal to mv squared over r. That's right. Which is equal to m times 2gh 1 minus sine theta. Right? All over h. Actually, it wasn't h, it's a rho. Is that right? Okay. So the m cancels, the rho cancels, and what this becomes is, and the g cancels, so it becomes sine theta is equal to 2 minus 2 sine theta, right? That means 3 sine theta of separation is equal to 2, right? And theta is equal to arc sine of 2 or 3. I didn't do much. I think Ted did a very good job. I just rewrote that. Okay? Now, coming back to this guy, we'll solve this for you. But here's the deal. I'm actually going to end now in a couple of minutes. But it's very simple. If you actually calculate velocity using energy and calculate theta using energy and plug it into this will turn out to be true. Because it's the same equation. You understand? So if you solve it this way and plug it into this will turn out to be true. Yeah?
The integration is using the same trick.
Yeah. Right. So if you use that and plug it in here, because the energy is like a pre-integration of a differential equation, right? If you plug it in here, of course it's going to turn out to be true. So that's actually also the solution to the differential equation. Now, differential equations of this sort, some of them can be solved in closed form by guessing, by tricks, etc. Some of them you have to use MATLAB for, right? That's the way it is. Really complicated systems use MATLAB. It's called simulation. Some of them you can do closed form and get some nice insights. This one you can do in closed form, and we'll give it to you as a handout. Yeah.
How do you do that equation where
How do we get that equation?
Well, how do you know that setting those two equals
It's a okay. So setting which two equal?
or plugging in r equals b squared.
Oh, how did we get that?
Well, I know how you get it.
Uh-huh.
How do you know that's going to be the angle where we
Oh, okay. So what we did here was we said, look, if you take a free body diagram here, right? We said there's some reaction force N. There is some force on this, mg, right? If you take components in this direction, that's mg sine theta, right? And this thing's got some acceleration, and the only acceleration inwards is v squared over r, right? Now I'm doing it in English. All I'm saying is, all Ted is saying actually is, hey, at what theta is the mg sine theta component barely enough to overcome the centripetal acceleration? Get it? At some point, it won't be enough, right? At some point, it's going to be not enough to keep this guy in a circle. And at 0, it's the point where it crosses over. Right? At some point, the reaction force will have to be a sticky force to keep the guy on the cliff. Right? So when the reaction force vanishes, is the point where gravity is keeping him down, where he transitions from that to somehow trying to hang on for dear life. Right? So that transition happens when n goes to 0. Answer your question? Did you have a question?
No.
Same thing? Okay. So, yep, DY?
I think I have a similar question. I think I have a different way of putting it that will make
Okay.
sense.
This was meant to be interactive, so we're interacting. Good, yeah.
Okay, so the assumption here is that at the top, the potential energy is 0.
That's right.
And then at the
No, it doesn't matter.
Sorry,
No,
it's not.
that's not an assumption.
Net energy is 0.
That's right.
The bottom of the potential energy.
Well, no, I would say it's slightly different.
Okay, the thing that I don't understand is how, so when you say 1/2 mg squared equals mgh minus y, you're saying that at any given point, the kinetic is equal to the potential, but that's not true.
No, no.
That's not true.
What's exactly being said? So actually, this is what you need to understand. Take the state on top. Take the state at which it's at some angle. Whatever potential energy the guy gained sliding down must have gone into kinetic energy and nowhere else. Very, very important. Potential energy is like a battery, all right? It's like a battery. This person is discharging the battery, but going down, right? And that's going into kinetic energy. It needn't have, if, for example, the person is losing energy to drag, to friction, right? Then energy is not conserved. But we're assuming energy is conserved. So drop in potential energy is increasing kinetic energy. Is everyone good with this? Copacetic with this? Right? Now, what I was going to say to you, this is a final comment is, differential equation. Painful to solve. No obvious, you can solve it and we'll solve it for you, right? But guess what? Pre-solved differential equation, energy. Only 1 degree of freedom, so energy is good enough. Solved. Insert it back in here. Hey, you have a solution for the differential equation if you want it. Get it? But it's no different. It's the same thing. Okay, done. So this is equations of motion. Next time we'll do angular momentum, and we'll get into rigid bodies and multiple particles. Lunch.